Okay, so we'll get started. So thanks to the organizers for inviting me to give this talk. So I'm going to talk to you about measuring the polarization of hadronic W bosons at the LHC. And this is work done with my PhD students, Songchap Takde and Will Shepard, who is at Sam Houston State. So you'll see that the first version of this paper was uploaded to the archive just after the pandemic started. But we have significantly updated our results, and we hope to put out a second version of the paper soon. Okay, so let me start with some very basic idea for the motivation for why we want to measure W boson polarization. And I'll try to convince you that's actually, in fact, one of the most important measurements that the LHC will actually make. The second thing I'll do is talk about how we'll measure the polarization using polarized Ws, first at the parton level to try to understand how you'd infer the polarization of the W if you knew everything about its parton level decays. And then in a detector, obviously what we see is different from the partons, but I'll show you how we constructed a proxy variable P theta, which allows us to infer something about the parton level distribution, and therefore allows us to reconstruct the polarization of the W boson. I will construct templates of this proxy variable, and then longitudinal W bosons will have a different template. Transverse W bosons will have a different template for this distribution, and that's what will allow us to separate the different polarization states of W bosons. And finally, I'll talk about how we construct some pseudo experiments to show the effectiveness of this tool to measure the polarization of W bosons and some results. Okay, so let's start with some motivation. Okay, so in the standard model, if you one of the main reasons the LHC was built was on a no-lose theorem, because if you have longitudinal W boson scattering without the Higgs boson, and remember this was before 2012, we did not know for sure if the Higgs boson exists or not, but we already know that longitudinal W scattering by itself is a problem. Massive vector bosons, their amplitude for their scattering grows with energy as energy square, so energy square over MW square. So at some energy, you run into problems with tree-level unitarity, okay, and your predictions break down for what the probability amplitude is. So in the standard model, this problem is resolved by the exchange of a Higgs boson, where this amplitude for this diagram also grows as the energy square, but it appears with a negative sign. More importantly, the coupling of this 4-point W boson vertex is exactly the same as these couplings, G, which show up in the Higgs coupling to W bosons. This is a very key feature because it allows for an exact cancellation between this bad high energy growth of these amplitudes, and therefore restores unitarity of the standard model. So the standard model is a unitary theory, okay, but we do not know whether the Higgs boson that we have seen at the experiment in 2012 is really the standard model of, is the Higgs boson of the standard model. As we heard yesterday, the degree of compositeness of this Higgs boson is measured to worse precision than that of a pion. So it's possible that these couplings, right now they're allowed to deviate by 10% from the standard model. Even a little bit of deviation would restore your problem of unitarity violation in these scattering amplitudes. So it's really important to measure this Higgs coupling to W's very precisely. So now, given that the Higgs coupling we don't know for sure how close this Higgs boson coupling is to the standard model prediction, you could imagine that it's scaled by some value A away from the standard model prediction, A is equal to 1 being the standard model value. So with this scaling, again, you would get an imperfect cancellation between these two amplitudes, and the scattering amplitude would again grow with energy. So you would like to measure, again, you would like to restore unitarity in some way. The theory should be unitary. It's one of those sacred principles that seems almost tautological. And one of the ways this can be done, if the Higgs boson is only partially responsible for unitarity restoration, is you could have something like a Techni-Rho exchange. This is in fact what analogous to in QCD, pion scattering is unitarized mainly by vector meson resonances. And so you could have a vector resonance coming in at some high energy scale, possibly even inaccessible at the LHC, okay? And but this could restore unitarity. But the way you detect the signatures of this is you would see this anomalous growth at high energies of WW scattering. In particular, anomalous growth of longitudinal W scattering, because the longitudinal modes are the ones that eat the Goldstone bosons. Okay, so it's really important to measure WW scattering at high energies. And in particular, you want to measure longitudinal W scattering at high energies, which is why it's important to measure the polarizations of W bosons. So let's talk about how you actually measure WW scattering at the LHC. So at the LHC, you're actually colliding protons and not W bosons, but these protons can radiate W bosons, and these W bosons can scatter with each other to go into another two W bosons. And along with this, you get two forward jets plus the decay products of these Ws. So this is a cross-section of the detector to show you what you would actually see in your experiment. You see two forward jets, those being these two jets, and you also see the decay products of these Ws. Since you're looking at high energy WW scattering, because of relativistic beaming, the decay products of this W tend to be collimated along this cone, and the decay products of the other W are collimated along this cone. Now, the current measurement of WW scattering is done typically using the semi-leptonic channel, okay, if you want to measure the polarization in VBS. The advantage of this technique is that, of course, you have relatively lower background because you're looking for a lepton plus missing energy and some jets. And one of the advantages is the missing neutrino kinematics is reconstructible up to a twofold ambiguity. So you fully know if this, let's say this W decays to lepton and neutrino, you can measure its polarization by looking at the angular distribution of its decay products. Even though you do not see the neutrino, you can reconstruct its momentum, and therefore you can reconstruct the polarization of the leptonically decaying W boson. Okay. The disadvantage of this is that the second W boson it has a polarization which you don't know. Okay. So you cannot measure the spin correlation between these two Ws. And since you're particularly interested in longitudinal W boson scattering, you cannot really test the unitarity of the scattering, okay, just by measuring the polarization of this W plus alone. So you really need to measure both the W boson polarizations, okay? So a possible solution could be to look at the WW in the fully leptonic channel where both decay leptonically. The problem with this is that you have too much missing energy. You have two missing neutrinos, and that does not allow you to reconstruct the decay products of this W or this W, and therefore you cannot reconstruct the polarizations. Or at least it becomes very, very difficult. Okay? So the alternative solution is to use the semi-leptonic channel where one decays to a lepton and neutrino, but you now make an ambitious attempt to measure the polarization of a W which is decaying to hadrons. Okay? And the advantage of this is that you have a higher branching fraction to hadrons compared to leptons. Okay, 70% of the time, a W boson will decay to hadrons. Both decay products are seen because you decay to quarks, and those quarks radiate, give you the shower. And you can see those decay products, at least in principle, you can use them to reconstruct the W polarization. So now what you can do is in semi-leptonic measurements, you can use the hadronic final states from this W. If you could, in principle, measure this polarization, you could get the spin correlation between these two Ws, and you can test for unitarity of longitudinal W scattering. Okay. The challenge with this kind of measurement is there are hadronic backgrounds to this, because your signal you're looking for is a lepton, neutrino, jet, and some jets from this W, maybe one or two. So it's lepton, missing ET, and jets, which has a large QCD background, okay, from let's say W plus jets. Yeah, that's the purpose of this talk, okay, is to explain how you will determine the polarization of a hadronic W. Okay. Okay. So the parton level W decay. Okay. Let me explain what you will do in principle at parton level, and then I'll talk about what you will do for the hadronically decaying W boson. So if you have a W boson, and let's imagine that it's moving along this direction. This is its boost axis in the lab frame, but now we're going to its rest frame. So in its rest frame, let's say it decays to quarks. So it decays to an up quark and a down bar quark. And the angle that the up quark makes is, let's say, theta star. Okay, this is in the rest frame of the W plus. Now, you can use simple angular momentum conservation arguments to argue that the amplitude for decay of this W boson into quarks at this particular angle theta star depends on the polarization of this W plus. So if the W plus is polarized right-handedly, the amplitude goes as 1 minus cosine theta star by 2. If the W plus is polarized left-handedly, it goes as 1 plus cosine theta star by 2. If it's longitudinally polarized, it goes as sine theta by root 2. What does this mean? It means that if your W plus is polarized this way, then you have a strong preference for cosine theta is equal to 0 is equal to -1, which would correspond to the up and down quarks being emitted along the boost axis. Okay, so that would be true if the W is transversely polarized. The preference is for the up and down quarks to be emitted along the boost axis. If the W plus is longitudinally polarized, there's a preference for the up and down bar quarks to be emitted perpendicular to the boost axis. Okay, so in principle, if you had access to this theta star, that is the angle in the rest frame of the W boson decay, you could infer the polarization of the W boson statistically. Okay, so now in principle, again, of course, now one of the things we know at hadron level is this will give rise to a jet, this will give rise to a jet, and those jets do not typically come with a charge, so you're not able to distinguish between which jet corresponds to the up quark and which corresponds to the down quark. So you cannot really tell the difference between theta star and pi minus theta star, or equivalently, you can't tell the difference between cosine theta star and minus cosine theta star. So what you can measure, at least in principle, would be d sigma by d mod cosine theta star. Okay, so what that means is you can't really distinguish between the plus minus polarizations, but you can tell the difference between transverse and longitudinal polarization. You can tell the difference between something where the quarks are preferentially emitted this way versus the quarks preferentially emitted this way. So you have some distribution of what, or some prediction of what you expect. So transversely polarized W bosons would have a distribution which goes as 1 plus mod cosine theta square. Longitudinally polarized W bosons would have a distribution which goes as 1 minus cosine theta square. So this is 1 minus cosine theta square. It's normalized by a factor of 3/2. And this is 1 plus cosine theta square normalized by 3/4. 0 being, 0 corresponds to emission this way, theta is 90 degrees, okay? Where, so there's a preference for longitudinal Ws to emit at 90 degrees, whereas for transverse Ws, there's a stronger preference to emit along the axis, the boost axis. So now, if you had access experimentally to the distribution of a statistical sample of W bosons decaying at various angles theta star, all you have to do is fit that distribution. So imagine this is the distribution that you get, and you knew this distribution, you would fit it to a linear combination of these templates, okay, of what you expect for transverse W bosons, what you expect for longitudinal W bosons, and you would extract out the transverse polarization fraction and the longitudinal polarization fraction as fit parameters, okay? So you can extract out those fit parameters and say that 80% of the W bosons in this sample, 80% are transversely polarized, 20% are longitudinally polarized, okay? Okay, so now what changes when you go to the hadron level? Okay, so the hadron level is much more complicated, okay, because you're not just looking at single quarks anymore. So a single quark in a detector actually first gives you a shower, okay, and so it radiates at the parton level. These partons combine into hadrons, and these hadrons eventually deposit their energy inside your calorimeter. So you get something called a jet. Okay, so and roughly speaking, this jet momentum should correspond to the momentum of that initial quark or gluon that initiated the jet. So now for a W boson which is decaying, you decay to 2 quarks, but depending on the boost of the W boson, the more boosted the W boson is, this jet which is coming out from each quark gets more and more collimated, okay, as you go to higher and higher boosts. So eventually, this spray of particles kind of merge together into a single spray, which you collect as a single jet at the LHC. Okay, so what you need to do is now you need to apply some kind of tagging algorithm to distinguish between this kind of boosted jet, which can arise from a W boson decay, and the jet initiated by single quarks or gluons, which come from QCD. Okay, so you want to separate out these two things, and within these kind of jets, you want to identify the polarization of these W bosons, okay, by learning something about the rest frame angular distribution of these quarks. Okay, so for those of you not familiar with jets, let me give you a quick primer on how jet, various algorithms that are applied at the LHC for jets. So there's this, the first step is to do what is called jet clustering, which is you collect all of these, the spray of particles in your detector, and you have an algorithm to combine them and decide which ones are close enough to be classified as a jet, okay? So since we're looking at these W bosons, you get what are called fat jets. So you need to use a large jet radius to cluster them, okay? So we use something called a Cambridge-Arkin algorithm with an R is equal to 1.0 to cluster these jets. The second thing that needs to be done is something called jet grooming. So besides radiation or these hadrons which come from the quark or gluon that you're interested in, you will also have soft radiation, which is which gives rise to softer energy deposits, but those are coming from your underlying event or pileup. And you want to remove those. So you want to remove these kind of soft and wide angle energy deposits. And these jet grooming algorithms allow you to remove this kind of soft stuff. What this does is it allows a better reconstruction of the jet mass. So now these two algorithms are applied to every single jet that you have in your experimental measurement. But in addition to this, you do something called jet tagging, which allows you to distinguish between these fat jets which come from W bosons and the kind of jets that you get from regular QCD. So the first jet tagging algorithm that you can apply is something called mass tagging, which is you simply demand that the jet mass, since it's initiated by a W boson, this fat jet should have a mass which is roughly that of the W boson. Okay, so you apply some kind of cut, let's say between 60 and 100 GeV of this jet mass, and you see a distribution here. This has a lot of QCD background, but you see a little excess here, and that excess is from fat jets which are initiated by a W boson. Okay, so in principle, this is one thing that you can do for jet tagging, but this is still not good enough. So you can still remove a lot more background of QCD by applying something called n-subjettiness tagging. So this is a typical jet, a cluster of energy deposits in the eta phi plane, so in pseudo rapidity and azimuth. What you can do is you can apply this algorithm for n-subjettiness tagging to identify whether this jet looks like it has two clusters or one cluster. Okay, so you see that this one is actually initiated by a W, and it seems to have two clusters, which you can see are pretty well separated from each other. This is a jet initiated by QCD, and it has more or less a single cluster, but the algorithm attempts to find two different clusters. Okay, and it quantifies how well it can find two clusters by a variable called the n-subjettiness ratio, tau2 by tau1, which is how two subjetty it is versus how one subjetty it is. And this number here is 0.29. This number here is 0.73. The lower the number, the more preference it is for having two distinct clusters in it. Okay, so this object looks more two subjetty. If you set some threshold cut, like let's say 0.3, then things which are below that cut, you call them W jets. Things which are above that cut, you call them QCD jets. Of course, some small amount of QCD jets will still pass as W bosons, and they will be some kind of background, okay, that you must account for. So when trying to measure the polarization, you will not only have longitudinal Ws and transverse Ws, you will also have this mix of background QCD, which you need to separate out. Okay, so now if we look at W boson polarization in the lab frame, okay, so if I boost my parton level kinematics to the lab, so now this up and down quark, okay, after a large boost, the up quark will, if the angle is acute, the up quark will have a larger momentum, whereas the down bar quark would have a slightly smaller momentum and be at a slightly wider angle. Okay, so now if I want to measure, remember I want to reconstruct this theta star, and that would tell me the polarization of this W boson, okay, statistically. So how do I reconstruct the polarization of this W boson from these final state quarks? And remember, these final state quarks are what are effectively giving rise to these subjets, okay? So one way you can do this, and this is what CMS has tried to do, is to use the opening angle between these quarks, or at the hadron level, the opening angle between these subjets, okay? The opening angle between these subjets is related to sine theta star, okay? So you can directly, from the measurement of this opening angle, you can try to get the value of theta star. However, this is not a very good variable to use because, for example, if you look at how theta opening behaves as a function of cosine theta star, it looks like this. It looks very flat, okay, for a large range of cosine theta star, and it looks even flatter as I go to large boosts, okay? So this is going up in energy of the W boson. So if I'm interested in measuring high energy W bosons and I try to measure the opening angle, you can see that if I make a small error in the measurement of the opening angle, I will make a large error in my inference of cosine theta star. So the traditional technique which has been used by the experiments is not a very good variable to use because you would make large errors on trying to reconstruct theta star, and therefore large errors on trying to reconstruct the polarization of the W boson. So instead, what we have done in our work is we proposed an alternative variable, and this variable doesn't suffer from the same problem. So it turns out that besides using the opening angle between these two subjects, you can also use, it turns out that there's this exact relationship, cosine theta star, is the difference in energies between these up and down bar quarks divided by the momentum of the W jet. So you can just see intuitively why this makes sense. Okay, so if you, for example, look at longitudinal Ws, where the quarks are emitted this way, theta star is 90 degrees, cosine theta star is 0. But in that case, when I boost them, since they're both perpendicular to the boost axis, they would end up having equal energy in the lab frame. Okay, and then the right-hand side would also be 0. So this works. And in the other case, when the W is transverse, so let's say the up is emitted here, the down bar is emitted here, theta is 0, cosine theta is 1, then the up carries all the energy, okay, and the down bar carries none of the energy when I boost to the lab frame. Okay, so delta E would just be the energy by momentum, and since this is assumed to be massless, this would be 1. Okay, so this is an exact relationship, so the claim is now that as a proxy variable, instead of trying to learn theta star from a measurement of the opening angle, you can use the energy difference between these subjects to learn about theta star, that rest frame opening angle, which is sensitive to the W boson polarization. Yeah. Yeah, I will talk about this. I will talk about that next. Okay, so you'll just see it in a slide or two. Okay, so what we do at the hadron level is we look at these jets. Okay, you look at the ones that pass your tagging cuts. And now that you have these subjects, this n subjectness algorithm returns those subjects for you. You take the energy difference between your subjects, divide by the momentum of this jet. That ratio is this proxy variable p theta, which is what we define. And this is a proxy for cosine theta star. Okay, at the hadron level, this is allowing you to infer exactly what cosine theta star should be. So one of these is a U bar, a U, and one of this is, you don't know which is which. That's why you're measuring mod cosine theta star, not cosine theta star itself. Yeah. Yeah, so mod is important, right? You cannot tell the difference between a positively and a negatively polarized W boson because of this, but you can only tell transverse versus longitudinal. Yeah. Okay, so now we construct templates of what this p theta distribution would look like. I'll skip over most of this, but we construct a theoretical simulation sample of pp to ww via scalar. This ends up giving you longitudinal w's, or via pseudoscalar resonance, and this gives you transverse w's. We simulate at parton level and mad graph, and then we do showering hadronization in Pythia. We don't really do a detector simulation at all, but we have some estimate of what the errors are due to detector effects. Okay, and then what we do is we take our W jets, which are boosted, and we reconstruct this p theta variable and construct its distribution. So in principle, p theta should reconstruct to cosine theta star, if I plot its distribution, it should look like 1 plus cosine theta, cosine square theta for longitudinal W's, 1 minus cosine square theta for transverse W's. Now, coming to the point that Tuhin raised, okay, the grooming algorithm actually biases you. So there are two distortions that you get in the distribution. One is your tagging efficiency is different depending on what cosine theta star is. The larger cosine theta star is, that means that the larger one of the emitted particles, the U or the D bar, is very soft and very wide angle, which means that it will fail the tagging cuts because your grooming algorithm, okay, removes so imagine one of this was a very low energy deposit, which is far away. Your grooming algorithm removes it, okay, and therefore it fails the tagging cut. So it would no longer pass the tagging cuts. And so you'd see that at large cosine theta star, you basically have very poor efficiency for selecting those kind of W's. So there's an inherent bias in like picking out objects with large cosine theta stars. In addition, your soft drop algorithm modulates, okay, your selection as of W bosons as a function of cosine theta star. Okay, so this is the 1 plus cosine theta square distribution. Yeah. Yes. Yes, I agree. Yes, that is true. But we have checked across different grooming algorithms. Okay, and now we have not simulated detector noise yet, but I'll give you some estimate and explain to you. Okay. So this is the 1 plus cosine theta square distribution, the idealized distribution. But because of your bias in your selection, okay, this would get modulated to something like this red curve over here. This is similarly for transverse W's. This is the ideal 1 minus cosine square theta distribution. But again, because of the bias of your selection effect, okay, you get a distribution that looks like this. Now, in addition to this, you could say, that I'm not really measuring cosine theta star, I'm measuring the proxy variable p theta, and we could look at the extra distortion that that would cause. But what we find is p theta is, so this is from Monte Carlo Truth, p theta excellently reconstructs cosine theta star, at least till cosine theta star is 0.8. Okay, so almost always p theta is gives you a very faithful reconstruction of this cosine theta star. Okay, so the only distortion really in the distribution away from 1 plus cosine squared theta is the selection effect of grooming algorithm plus your tagging cuts. Okay. Okay, so finally what we get is we get these templates. Okay, so we get this template for longitudinal W bosons, this template for transverse W bosons, and we also simulated what you get for background QCD. Okay, and you get this kind of template. So in principle, I could do now a fit to all these three kind of distributions. Okay, and try to extract what fraction of the jets that I'm seeing are longitudinal Ws versus transverse Ws versus background. Yeah. Yeah, so I'll just say something about this. So I'm going to show you the discriminatory power. But before that, actually what we did was, this is where we apply a fixed cut on n sub jettiness. So instead of applying a cut on n sub jettiness, we only apply a mass tagging cut. And rather we look at the 2D distribution of this proxy variable p theta and this tau 2 1 variable. Okay, and when you look at both of these together, then you see a big difference between longitudinal Ws, transverse Ws, and tau 2 and background. Because if I just applied a cut here to reject background, okay, then the distributions for, let's say, longitudinal, transverse, and the background, they do not look all that different. But if I look at the 2D correlations, I really see that there's very big differences. So instead of using 1D templates, we actually end up using these 2D templates, okay, to discriminate. So, so quickly applying this to the main purpose, which is vector boson scattering at the LHC, we just do a quick estimate, okay, of the number of events that we expect to see at the 13 TeV LHC with 3,000 inverse femtobarns of data. So I took the current CMS study, which is at 138 inverse femtobarns, and scaled it up. So the QCD background events roughly you'd expect with 3,000 inverse femtobarns is about 32,000, out of which you'll have 2,000 hadronic boosted W events. Sorry, this would be your signal, this would be your background. So, and let's say you have 20% longitudinal W. So you would have 400% longitudinal, 1,600 transverse. So now what we can do is we generate pseudo data by taking a linear combination of the longitudinal, transverse, and background templates in this ratio, 400, 1,600, 32,000, and we get the sum. We add Poissonian noise, okay, and that gives us this distribution. So this is what we consider pseudo data. Now we take our pseudo data, and now we try to decompose the pseudo data into those templates, into linear combinations of these templates by doing a fit, okay? And so we try to reconstruct these numbers, 400, 1,600, and 32,000, and this is what we get, okay? 480 plus minus 140, 1,671 plus minus 140, and so on. So rather than looking at absolute numbers, let's look at the polarization fraction. The true polarization fraction of longitudinal Ws is, true fraction of longitudinal Ws is 1.8%, and true fraction of transverse Ws is 4.7%. The rest is all background, right? Your background dominated. When we reconstruct in the pseudo experiment, we reconstruct fairly well within 1 sigma, okay, and the error is also pretty small. So the polarization fraction can be extracted at about the 10 to 30% level in these hadronic decays at the high luminosity LHC. Okay, we repeated this for many pseudo experiments to check that this makes sense. So these results are using p theta and tau 2 1 alone, and it can be further improved with a multivariate analysis fitting for the kinematic distributions. So let me conclude by saying that the measurement of W polarization in hadronic channels is extremely important for understanding the unitarity of vector boson scattering. So besides measuring the Higgs couplings, unitarity of vector boson scattering is probably one of the most important things that the LHC will measure. Okay, and what we have done is we've constructed a new proxy variable which is sensitive to the polarization of these boosted hadronic Ws, which will allow you to test this unitarity of longitudinal W scattering. It uses jet substructure techniques to measure the energy difference of the subjets, which is much more reliable as a way to reconstruct cosine theta star than the opening angle currently used by CMS. And we expect to be able to reconstruct the polarization fractions of W bosons to within something like 10 to 30% at the high luminosity LHC with 3 autobarn inverse of data. And this tool is, of course, I gave you one application, which is WW scattering, but there are many other applications for this tool. You could use it for new resonance searches decaying to WW. If I want to know whether it's a scalar or pseudo-scalar resonance, I could use it to measure polarizations of tops in top decay. Okay, thank you.
Okay. Thank you. Questions, comments?
Thanks. Just one naive question. Actually, two questions. The first one, you wanted to look at WL, WL to WL, WL. Fine. You have reconstructed or differentiated between WLs and WTs in the final state. Now, initial state Ws, do you know whether, I mean, how do you know whether they're WTs or WLs?
Yeah, so strictly speaking, you cannot measure that. Though what you have to do is you look at the polarization combinations, the spin correlation of all final states. So you look at all final state combinations, longitudinal, transverse, 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 longitudinal, longitudinal. And that fraction is sensitive to all the different combinations of transverse, transverse scattering to transverse, transverse, longitudinal, 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 and so on. So you don't fully test exactly longitudinal, longitudinal, but you test more combinations of different possibilities.
And is that information going to be enough for looking at this perturbative unitarity?
Of perturbative unitarity?
I mean, that's what one of your goals is, right? To look at the unitarity.
Well, you'll more strongly constrain it, let's say, than if you did not use this measurement.
Okay, fine. I have to think a little more about that. My second question, have you thought of, or is it feasible even to look at WW to TT bar?
And measure the polarization in the final?
Well, maybe not measure polarization, even just to look, identify WW to TT bar, because that too is going to show a loss of unitarity, maybe not as strongly as WW to WW, but it will still show, if you have a change in the Higgs couplings or change, you introduce a technique rho.
My naive guess would be you would be heavily background dominated by QCD production of TT bar.
Right.
So
it would be, but if you go in for the boosted guys, would that be of any use? Because you also want a boosted
again,
stuff here.
electroweak production, I think, would be far subdominant even at high energies. Right? TT bar is just strongly.
Yes.
If you use VBF kinematics cuts, I mean, otherwise you wouldn't do any VBF measurement if you were going to be down, down.
No, but VBF is, there's no strong production channel, right? There's
glue into Higgs is a strong production, right? I mean, it's not
I mean, that's very weak coupling, right? So
no, but I mean, what I'm really trying to say is that that kinematic region is so spectacular that this it may need not be hopeless. Exactly. No, it doesn't, because if the glues do that,
the beam is connected to two jets and TT bar in the middle, no? With a glue coming.
Yeah, but the point that I'm making is that when it is a W, you don't have a hadronic activity, no? That's what I mean by the.
You are looking for TT bar plus jets.
No, but the point I'm making is that there is no hadronic connection between when it is a. Perhaps that is not correct, because when it is a top, I will have additional emissions in the rapidity space.
Okay, so, sorry, let's go to the next question. Gagan.
So very naive question. The fact you have two forward jet, and as you know that in the high luminosity phase, we'll have high granularity calorimeter. And so the thing is, how would it help, for your background suppression and indirectly affecting your sensitivity of this, the cos theta star modulus, whatever you were saying. So how much that will help? If
you're asking about how, so if I understand your question, you're asking how does identification of these two forward jets help you suppress the background?
Exactly.
Yeah, so typically what you demand, so let me get that picture of, the detector. So what you demand is that you have these two forward jets, okay, which have a large pseudo rapidity separation. They are high PT jets, okay, and they have a large, high PT in the sense maybe greater than 30 GeV or whatever cut you said, and they have a large invariant mass, okay. All of these together are very hard to replicate. I mean, you still have a lot of background QCD, but you can suppress a lot of it. Yeah, so let me in fact show you the CMS result, okay, which I have on one slide, right? So this is the current measurement of VBF. So this is the current measurement of VBF. This is based on the invariant mass of those two forward jets. And you see this is the background, okay, which is dominated by W plus jets. And it falls off as I go to high invariant mass. But if I look at the signal for W boson scattering, that doesn't fall off as fast, okay, as this falls off. So the higher the cut, the more you can suppress this background.
Okay, Dipankar.
Sorry, I'm confused here. So this is for when you say there's no hadronic activity in between the jets. Have one W is actually hadronic. So this would
No, this is W plus jets, right? So semi-leptonic.
semi-leptonic. Okay.
Yeah.
Both semi-leptonic.
No, semi-leptonic means one is decaying to leptons in
What
the.
I meant by that, but you still have hadronic activity in between the forward jets, no?
You will have some, yes.
That is not going to pass you.
That's not going to pass.
Apple versus orange, no?
No, I don't understand. What
So
exactly?
your one of the W is hadronic.
Yes, one is hadronic.
So you have the veto is not working, no?
I'm not. What am I trying to veto? I'm trying to veto background, right? I'm trying to veto. W plus
Hadronic
jets.
activity in between two forward jets.
Yes.
So, but I'm confused. Am I missing something? But my signal doesn't pass that cut, no?
No, I'm not. Okay, it's large invariant mass for these two jets. Other hadronic activity
That is
can.
by definition because they are back to back or
Yeah,
large rapidity.
that's.
So all events will have large invariant mass between them.
No, but you see it has this distribution, right? So this is the distribution for WW scattering. This is the distribution for background, right? For background, that will not be the case, right? For background, the jets will be produced at all angles. So the likelihood that you have a large invariant mass is smaller at high invariant mass.
Dipankar.
Yeah, the signal is quite small. Like even here, right? You have 2000 hadronic boosted Ws compared to 32,000 background, right? So within this, we're claiming that you can still measure the polarization fraction.
Oh, one question you showed about this composition of QCT jets, your W transverse and longitudinal.
Yeah.
Now in between will come the detector noise.
Yes.
How well you think you have done that? I mean,
Yeah, so I have one backup slide to show on this. We haven't done the study carefully, but I can tell you what we have, okay? So this is the error on that proxy variable P theta. And the error would come from the how well you can measure the energies of the subjects, because P theta is constructed by an energy difference between the subjects. So that error would be some order 1 factor times the error resolution of the subjects, okay? This error resolution, there's no published error resolution for subjects, but if you use the jet energy resolution, that is about 10%, okay? So, so which means that P theta, roughly speaking, so I don't know whether there's a, I'm not claiming that this is what you will get for subjects. I'm saying if you assume this is what you get for subjects, then this can be measured to within 0.1, and that is roughly the binning that we used on P theta when doing the fits. Okay, because you'll make that much will be a smearing on P theta.
Okay, there's another question.
Sorry, one small question. Maybe taking cues from the previous question. So when you talked about this WW scattering, instead of actually like motivating it as a mean to probe the WWH coupling, since we already somehow, and to some degree, we know the WWH coupling from Higgs data, right, from signal strengths. So we can use that as an input and then instead try to verify that WW quartic coupling instead, whether that is actually G square. So would this scattering be, can it be motivated to actually check the SU2 nature of the W boson? Like instead of, since you already know WWH from an independent source, can you try to motivate it just to probe that quartic coupling, direct quartic coupling? And
yeah, that's a good question. So people try to do this with triple gauge boson couplings, because so WW scattering will also have triple gauge boson coupling.
Yes, that.
So you're asking, can you actually measure the quartic in?
Yeah, so it would be a independent cross check of the quartic coupling, and if the quartic coupling turns out to be the pure SU2 gauge coupling, then you are sure about the pure SU2 nature of the W boson, because you know the WWH coupling from an independent source now. So can you basically turn the
yeah, I suppose you could do a global fit to WW scattering and Higgs couplings to check this. Yes, because the Higgs coupling to W's has error also, right?
Yeah.
You need to do a global fit to both.
All right. Okay.
one question is that, do you have plan to implement it in a sort of a data-driven way, in a sense that without relying on simulation for your templates, did you think of having it?
So we had a couple of ideas that the referees were not happy with, okay, to use W plus jets and things like that. But the backgrounds basically are the issue, whether you'll get a pure sample of longitudinal Ws in your detector. Is there anything that gives you pure samples of longitudinal Ws or transverse Ws? And it's not very clear that you can do that from purely data-driven way. Because you'll still have QC decontamination even in those samples. The transverse. Mm-hmm. Yeah. Yeah.
Okay, I don't see any other hands raised. So let us thank the speaker and